All right, good morning. Hope your weekend went well. Um, let's see. My son Jack is taking a math test today for which he is somewhat not well prepared. We were spending the weekend, we spent hours together. He's having to learn how to graph cosine and sine functions, but they don't want to stop there. They're making him do like tangent, and then who's ever heard of secant or cosecant? You have, because before this weekend I was like only vaguely aware, but anyway, uh, it's like great. I get to be in high school again and do high school homework again, but it was really hard. So. I'm sure you feel really sympathetic to me now that I sent you home with all kinds of stuff to do to get ready for your exam, which, by the way, closes today, so good luck. I think about 17 of you have taken it yet, so yes, the testing center schedule is weird in the spring term, so pay attention to closing times. All right. So we're going to talk today about non-covalent interactions, which are key to understanding the world around you. We're also going to talk about the shapes of molecules and rotation around carbon-carbon bonds. So the term non-covalent interactions is a catch-all for interactions among these types of things, and you can basically mix and match all of these types of things with each other. For example, you can have ions interacting with themselves. You could have ions interacting with dipoles or with induced dipoles or with quadrupoles. And you could do the same for dipoles and so on. The basic principle here is opposite charges attract, like charges repel. Ions, we're talking about point charges. So, your example, sodium and chloride. Dipoles, we're talking about really just distribution of charge along a line. So an example of a dipole would be in HCl. There's a dipole because chloro is more electronegative than hydrogen. We represent the dipole with a line that goes like this with the arrow towards the negative end. Another way of looking at that would be to write a delta plus near the hydrogen and a delta minus near the chloride. Another way to visualize dipoles would simply be to come over here to Spartan and look at what's called the electrostatic potential surface, and this uses color to represent areas of partial positive charge versus negative charge. So you can see the blue color of the hydrogen indicates positive electrostatic potential, or that this is the electron poor part of the molecule, and then the darker yellow and green color here represents that this is the more electronegative or electron-rich part of the molecule. Okay, questions about the definition of a dipole? Easy, done that before tons of times, right. Induced dipoles are another weird type of thing. We see these most often with things that are not very polar in and of themselves. Molecules that have dipoles or charges are often called polar. But if we draw, say, this hydrocarbon, the difference in electronegativity between carbon and hydrogen is small, such that there isn't much of a dipole in this molecule. Nevertheless, if we envision the electron density surrounding this molecule, what we would see would be something like this, sort of a cloud of electron density associated with each carbon-hydrogen bond, and that cloud of electron density is not a hard little sphere. It's more malleable than that. And so that electron cloud can fluctuate temporarily so that along one side of the molecule there's a slight excess of let's say positive charge, and we'll use the blue color to represent positive, and then the red color to represent negative. This is temporary and transient dipole due to what we're going to call electron cloud polarization, which simply means the electron cloud is leaning a little bit towards one side. Yeah?
So, like, would that polarization be caused, like, for example, say like a chlorine ion just got close to it, would it shift the electrons away?
Yes. Yeah, great question. So how might this occur? It can occur instantaneously with time, but it often occurs in response to the presence of other nearby molecules. So, as you point out, if, say, we had a chloro that was negatively charged and it's suddenly near this molecule, probably the molecule rearranges its electron density to be more complementary to its surrounding. Okay? Yeah.
Sorry, in that case, that side would stay positive.
That side would stay positive. In contrast, if we moved it to the other side, we'd switch it. Yep. So as we go from point charges to dipoles to induced dipoles, the interactions get weaker because the point charge is all in one place. The dipole has not a full charge but on one side versus the other, but it's distributed along a line, partial charges. And then the induced dipole isn't permanent, and so that sort of makes you go from stronger to weaker types of interactions. So those are the three basic ingredients that your text deals with. I wanted to introduce one more, which is important to the world of organic chemistry. And I don't really know where to put this in terms of strong versus weak. I'm going to basically put it equivalent with a dipole. What do I mean by a quadrupole? A quadrupole is a distribution of electron density not along a line. And I'm not sure how to... But in 3D maybe is the way to talk about that. So the classic example of a quadrupole or a quadrupolar molecule is benzene. Benzene is thought of as a non-polar solvent, and it is. It's non-polar for the following reason. Carbons, if you remember, sp2 hybridized carbons are more electronegative than hydrogen because the sp2 hybridized carbon has more S character and holds electrons closer. What that means is that each carbon-hydrogen bond creates a mini dipole with positive end near the hydrogen. Now, benzene, however, is symmetric, and what that means is that each mini carbon-hydrogen dipole is canceled out by another mini carbon-hydrogen dipole on the other side of the molecule. Okay? So each of these bonds individually is polar, but because of the symmetry of the molecule, they all cancel each other out, and overall, benzene has net 0 for a dipole. Okay? Nevertheless, it would be incorrect to say that the distribution of electron density around the benzene ring is uniform, because what this picture here predicts is that the hydrogens should be electron poor. The color we're using for that, I guess, is blue. So the hydrogens should be somewhat electron poor, whereas the carbons should be electron rich. Okay? And so that's not a line, it's sort of a circular non-uniform distribution of electron density. If we looked at the benzene ring from the side, with this stuff in the that I'm highlighting sort of coming out toward us, we would see that the edge, the benzene ring is flat, and the edge of the ring, as represented by these carbon-hydrogen bonds, is electron poor, but the faces of the ring, both above and below, are electron rich. And you can see this in an image that I'll show you from the Spartan program. Let's just go back here. Yes. There's benzene. And then I'm going to click on this, which gives us what's called the electrostatic potential map. And again, colors that are lighter represent positive electrostatic potential or electron poor locations, whereas areas that are yellow are more negative. Do you see how it's minus 80 here on the face of the ring? That means electron rich, whereas it's plus 57 or something on the hydrogens. Okay? So you should be used to thinking about molecules like benzene as being nonpolar, but having this quadrupolar characteristic where the face of the ring is electron rich. This has consequences in chemistry and biology. And scientists have known for quite a long time now, and you can do actually calculations to demonstrate this, that if you take a benzene ring in the gas phase and you allow it to be near, say, a potassium ion, and the potassium ion sort of like this, you can actually get a complex in which the potassium ion sits down on the benzene ring and is attracted to it. And it turns out the strength of that interaction is stronger in the gas phase than the interaction of potassium ion with water, which is sort of shocking, actually. You think, okay, it makes sense that potassium ion should like to interact with water. You know, that would be an example of an ion-dipole interaction, wherein water, oxygen being more electronegative than hydrogen, the oxygen has a partial negative charge. The net dipole of the molecule is in this direction. But if you measure the strength of the interaction, it's actually stronger for the interaction of potassium with benzene. And it's because that positively charged potassium ion is sitting down on this electron-rich face of the benzene ring. People call this a cation pi interaction. Pi is for the benzene ring and these pi bonds, which create a delocalized system of pi molecular orbitals that we'll deal with in a later chapter. But this is a classic interaction that's found actually in a lot of proteins in biology. So acetylcholine esterase enzymes and acetylcholine receptors use this type of interaction in the signaling of, use this as a way to bind acetylcholine, which is involved in neurotransmission. Go ahead.
So you said which one was stronger, though?
In the gas phase, this one's actually a little stronger. And the numbers aren't particularly important, and the fact that one is stronger than the other is also not important. I'm just trying to give you a sense for how impactful that is. Yeah.
Just a question back on induced dipoles.
Yeah.
I understand that that whole electron cloud can be moved by another particle coming in, some positive and negative charge, but are you saying that it kind of randomly is just the flow of the cloud is one side's positive, one side's negative?
Yeah, I mean, so these types of interactions are induced dipoles are most important as molecules approach each other. If you've got one molecule alone in a vacuum, I suppose it's possible that the electron cloud is fluctuating with some amount, but it really is a bigger deal when molecules come closer together. So let's actually talk about that kind of interaction now. So this one is painful to write. It's an induced dipole interaction with another induced dipole. Okay, and what happens here, this is complementary. This is an issue of complementary induced dipoles. These types of interactions are also called London dispersion forces, and they are also sometimes called van der Waals interactions. All of those are used interchangeably. And the idea is that if I bring two molecules together, the electrons in one molecule and the electrons in the other molecule will actually start moving in a correlated way. The basis for that is actually embedded in quantum mechanics. There is favorableness that you get when electrons move in a correlated way that allows them to minimize the repulsion that an electron feels for another electron. And so as two molecules approach each other, automatically they will tend to rearrange their electron density so as to be complementary along the areas where they are close to each other. Now that's not to say that this northern hemisphere of this molecule is always electron poor and this southern hemisphere of this molecule is always electron rich. No, it switches back and forth and happens instantaneously, but the electron density along this northern hemisphere and this southern hemisphere tend to be complementary. Yeah?
And so, like, over time, they would stay bonded because of that?
Over time, they would stay near each other.
Because we talked about that.
Yeah, and it's not a full covalent bond, but it is a lowering of energy upon being near each other. Okay? So this interaction depends on molecules being near each other and really in contact. There's the term van der Waals is often used. You'll hear about the van der Waals radius of an atom, which tells you about how big an atom is. And that's the radius at which electron-electron repulsion starts to overcome these attractive interactions between induced dipoles. In other words, I can make a complementary interaction to some point, but if I go past a certain point, then I've got charge repulsion dominating and the molecules will push farther apart. So the van der Waals radius is really as close as atoms can get to each other if they're not bonded to each other. And again, it's a trade-off. If you get somewhat close, you get these complementary interactions between induced dipoles. If you get too close, the repulsion between electrons overcomes that. All right.
So,
yeah.
Sorry, another question. So if like an induced dipole were to go benzene ring.
Uh-huh.
Would that interact in the way that it would stay close to it as well? Or since like the induced dipole is like constantly changing, would it like be attracted and then release?
That's interesting. So by constantly changing, I guess I mean if you have two induced dipoles, there's no reason for one to be negative here and the other to be positive there permanently.
Yeah.
And so they can flip back and forth as long as they're complementary. In contrast, if you take something like, let's make it simple. Well, no, that's fine. If you envision a benzene ring, and shoot, I meant to draw this as though we were looking at it on its side. All right. Electron poor face, I'm sorry, electron poor edge, electron rich face. And then you bring this hydrocarbon close to it. What do you predict the electron cloud of the hydrocarbon is going to do as it approaches the face of the benzene ring? Sure, yeah, it should shift so that as it contacts the face of the ring, it's complementary, and as it contacts the edge of the ring, it's complementary in that way. And again, that's a weak interaction because there are limits to how much this hydrocarbon can distort its electron density. Nevertheless, it's enough to be pretty impactful. Yeah. So this is what I mean by mix and match. I could take an ion. We talked about that at the very beginning. I could take an ion and do the same sort of thing. I could take a dipole and do the same sort of thing. All right? Yeah. Questions so far? Yeah.
This is like a clarification a while back. Just with those carbon-hydrogen bonds, the reason why it's dipole is normally it's pretty equal, but because it's an sp2 carbon, it's closer to the carbon equal to it's closer.
Right. Yeah, the principle here, and maybe one that you haven't learned yet, is that sp2 carbons are actually more electronegative than hydrogen. Yeah. Okay. So a couple of, as I said, you can mix and match these. You can interact ions with dipoles or with induced dipoles and vice versa. A classic example, we've talked about induced dipole interactions. A classic example of a dipole interaction is the hydrogen bond. You've heard of hydrogen bonding before, and it's possible it's been introduced to you as something different than a dipole-dipole interaction, but actually it's just a special kind of dipole-dipole interaction. The hydrogen bond involves interaction of an electronegative atom, such as this oxygen, in a water molecule, with a hydrogen atom in another molecule where that hydrogen atom is electron poor. Okay, we'll sometimes represent that by a dotted line, but all we're really talking about here is this hydrogen is electron poor and this oxygen is electron rich, and so they're attracted to each other. Okay? No more complicated than that, really. Hydrogen bond types of dipole-dipole interactions tend to be more important than, say, other kinds of dipole-dipole interactions. Acetone is this molecule I've drawn here. it likewise has a dipole oriented in this direction, and so the dipoles could align so that the partial positive charge on this end is close to the partial negative charge on that end. But these two acetone molecules cannot get, because carbon is bigger than hydrogen, they can't get as close to each other as the dipoles can get here. The dipole, or the electronegative oxygen atom can actually get quite close to this hydrogen atom. And one general principle for these non-covalent interactions is they all depend on distance. And their distance dependencies vary, but for all of them, farther apart is weaker than close together. So the hydrogen bond is particularly strong because hydrogen is small, so the dipoles can get closer together than other kinds of dipoles. Let's see, there was more to say about the hydrogen bond. Some people like to think of the hydrogen bond as being partially covalent in character. And to envision this, all you have to do is draw the HOMO of one water molecule, which would be a non-bonding lone pair. And if we want to imagine that being in an sp3 kind of orbital, that's totally fine. And then we can draw on the other water molecule the hydrogen-oxygen sigma star antibonding orbital. And so we might actually conceive of the hydrogen bond as being partial, not complete, but partial covalent overlap, partial overlap of the filled orbital with the empty orbital. Okay, questions about that? Yeah. Yes. So hydrogen bonding happens in particular because of the electronegativity of whatever atom hydrogen's bonded to. So you might predict the strength of various hydrogen bonds, struggling to write, based on the electronegativity of the atom. So you would predict, for example, that hydrogen bonds involving oxygen would be stronger than those involving nitrogen because there'd be a bigger charge distribution for the oxygen than for the nitrogen.
So does it only bond to this 3?
So, well, be careful what you mean by bond. The question is, does hydrogen only form hydrogen bonds with those? Well, first of all, the hydrogen is covalently bonded to something else. The thing that makes the hydrogen bond possible is that that something else is more electronegative. So the hydrogen has a partial positive charge on it, and then something else that's electronegative can interact with that in a not full covalent interaction. But yes, the other atom has to be electronegative. One way to recognize hydrogen bonds, and this is one of the reasons people say that these have partial covalent character, is that attraction is strong enough that it overcomes some electron-electron repulsion. And in the case of hydrogen bonds, the atoms actually get closer together than would be allowed based on what's called the van der Waals radius. And so that's one of the ways you can tell that hydrogen bonding is occurring if you see the structure of a molecule, and there's experimental techniques that allow you to do that, is if the atoms are closer together than you would expect otherwise. Hydrogen bonds in water are ubiquitous but are short-lived and transient. So what that means is water is not a rigid network of hydrogen bonds. We can tell that that's the case because water is a liquid, right? So if you zoom in and look at ice at the atomic level, what you see for ice is that each oxygen can form 2 hydrogen bonds with nearby hydrogens. I'm going to draw those hydrogens here. Oops. And then each of those hydrogens belongs to another oxygen, which can be bonded to another hydrogen. And then each oxygen has lone pairs again that can bond to form a hydrogen bond with another hydrogen atom. And so the network can continue on indefinitely. And I'm not drawing as many as I could, but you can form this sort of tetrahedral lattice of water molecules where the oxygen has two covalent bonds with two hydrogens and two non-covalent hydrogen bonding interactions with two other hydrogens. Incidentally, this is a 6-membered ring, and that kind of pattern is responsible for the hexagonal shape of snowflakes. So that's kind of cool. One other interesting thing is that which hydrogens are covalently bound versus which are not gets kind of murky. For example, you can see that it wouldn't take very much at all for this hydrogen to slide over here such that this hydrogen would now be covalently bound there and hydrogen bound there. And similarly, this oxygen could steal a hydrogen from another source, and another water molecule could steal this hydrogen from another source. And so there's lots of exchange of covalent versus non-covalent interactions in water. What we mean by this is water molecules are constantly doing the proton shuffle where, oh, no, that belonged to you, that belongs to me, and we're trading back again. What that means is if you have a beaker of water and you put a single molecule of H3O plus in it, as soon as it gets in there, you no longer have any idea where that H3O plus is. All you know is you have a beaker of water with one extra proton that's being shuttled around and traded. And at any moment, maybe this water molecule is positively charged, but then we rearrange things, and then now it's this one through swapping of protons. Okay, yeah?
And is this also the reason why ice is less dense than water?
Yes.
It's very strictly versus water, which can shift around and temporarily have more bonds?
Right, that's a great question. Is this why ice is less dense than liquid water? Yes, the rigid network of hydrogen bonds requires more space between water molecules than it would if the water molecules were free to flop around and trade partners. Yep. So this is why ice floats, which is convenient for our universe, because if it weren't, all of the lakes would start to freeze from the bottom up. And then eventually we would, die. There's probably death is always the, sorry, I don't know why we went there, but go ahead.
So the swapping of protons does not happen.
Well, the question is, does the swapping of protons happen in ice? It probably depends on the temperature. I would just say in ice, the water molecules are moving slowly enough. They're probably jittering around in their crystal lattices like this, but they're not moving a lot with respect to each other. I don't actually know if they can trade protons. It seems to me like it would be pretty easy because all you have to do is slide one proton down here and then everybody else adjusts. I don't know. The one thing that I didn't learn until fairly recently is that temperature is just a measure of molecular kinetic energy. That is how fast the molecules are moving in solution. So the thing that differentiates ice from liquid water is the fact that the water molecules in liquid water have more kinetic energy, which becomes motion relative to each other. That's translational motion. You also have tumbling and rotational motion. So there's more of that in liquid water than there is in ice. Let's see. And that allows us to say something about how these non-covalent interactions relate to physical properties of molecules that we deal with. In general, non-covalent interactions affect the state of the physical state of various molecules. So a classic example is sodium chloride, NaCl, is a solid. In other words, and what that means is the ion-ion interactions are strong enough to keep the sodium and chloride ions close to each other instead of tumbling rapidly relative to each other as they would in a liquid, or blasting off into the vacuum of space as they would in a gas and being infinitely separated from each other. In contrast, water, which has a dipole, at least at room temperature, is a liquid. And what does that mean? Well, that means the dipole-dipole interactions between water molecules, or the hydrogen bonding, are strong enough to limit the ability of water molecules to move around relative to each other. They can tumble around and move side to side relative to each other, but the dipole-dipole interactions keep them close enough together that they're not just flying off at infinite distance into the vacuum of space, at least at room temperature. And of course, evaporation happens all the time, and we could talk about that, but we won't. Then let's talk about, say, butane. It's this hydrocarbon. It can have induced dipole interactions with itself. What is the physical state of butane at room temperature? What do you know? It's a gas, right? You want to buy butane, you don't buy a bottle of liquid butane, you buy a compressed cylinder of butane. And then when you use it, it's kind of like a blowtorch. In fact, my son yesterday made creme brulee for his mom for Mother's Day. And he texts my sister and says, "Do you have a blowtorch?" And she says, "No, but I'm kind of curious as to what's on the other side of that question." And so anyway, we went over to my mom and dad's for dinner, and Nate brought these custards that he had baked, but my dad happened to have a blowtorch. So Nathan fires that thing up and is using the blowtorch to caramelize the sugar. And it turns out, if you want to know, the secret to a nice glaze on top of a creme brulee is a thin layer of sugar. If you do too much sugar, it takes too much torching to melt it, and then the sugar starts to burn and smoke a little bit. We know this a little bit. We know this from experience now, and but the sugar that's slightly burned still tastes good, which I know from experience because I'm the one that had to eat the sugar that was burned. Anyway, it kind of had it was sugary, but it kind of had a smoky flavor. I don't know. Yeah, a bit more carbon. All right, so butane is a gas. The reason butane is a gas is because the weaker induced dipole interactions available to butane are not strong enough to overcome the kinetic energy of butane molecules at room temperature and keep them close to each other. Okay? So you're going to see the strength of a non-covalent interaction is a pretty good predictor of whether something's going to be a solid, a liquid, or a gas. All right. There's a few other things I want to talk about as it relates to these interactions. I want to show you some examples of hydrogen bonding and induced dipole interactions, but I also want to talk about strength in context. So when we talk about the interaction between two things and we say, how strong is it? The answer to that question depends on what the comparison state is. All right? So let's start, and we alluded to this last time, but let's start with sodium chloride in the crystalline lattice, in which each sodium ion is potentially surrounded by six other chloride ions. 1, 2, 3. I don't know where I got 6 from. I'm not. Oh, there's one in the front. Maybe that's 6. Anyway, you have this cubic crystalline lattice where each sodium is surrounded by like 6 chlorines, and each chlorine is surrounded by 6 sodiums. And those are ion-ion interactions, and they're governed by Coulomb's law, which tells you that the energy of the interaction is related to some constant, and then you've got the charge on one, the charge on the other, and then the distance between the two. But this equation for that energy is relative to infinite distance between the two ions. In other words, the reference state is the two ions so far apart that they no longer see each other. Okay, so if that's your reference state, what we're really talking about here when we say how strong an ion-ion interaction is that it's really hard to boil sodium chloride and get the sodium and chloride ions to be infinitely separated in a vacuum. Which is fair enough, but that reference state has very little bearing on us on a planet with lots of water and with an atmosphere. In space, maybe. But this is what I was saying last time. If you take sodium chloride and you add water, sodium chloride dissolves in water, and you have in the place of all of the previous ion-ion interactions, you have many more ion-dipole interactions. This is difficult to represent in 3 dimensions, so I'm not really going to try. You have the positively charged sodium ion lined up with the negative end of the water dipoles. And so the question is, how strong is the sodium chloride ionic interaction in the crystalline state relative to being dissolved in water? And the answer is it's not, in the sense that you can fully replace the strength of this interaction in the crystalline state with other interactions that you form in solution. Okay, you replace dissolving of sodium chloride involves replacing sodium chloride ion-ion interactions with many sodium water and chloride water ion dipole interactions. Yeah.
This is kind of off topic from what you're saying, but I just was wondering if, like, in this reaction with dissolving, if having like more like water molecules interacting with the sodium
Uh-huh.
might have an effect on each other. Does that make the interaction with one water like less
Oh.
powerful or more powerful because there's like intergenerative core?
Right. That's an interesting question. You could imagine a single sodium ion interacting with a single water molecule.
Yes.
What is the strength of that interaction per water versus having multiple water molecules? I don't know. It's a good question. And this really gets to an issue that you learned about in general chemistry, and that is whether a process is spontaneous or not, whether you can expect it to occur, whether that process is downhill in free energy. But before we deal with that issue, other questions about what we're seeing here? Yeah.
So that's kind of the same idea of why for the quadruple,
Yeah.
right? Quadruple interaction with like the cation and benzene.
Yeah.
Why that would be more favorable than the cation with water? Probably because benzene can have more surrounding it.
Yeah, I mean, I don't know the reason why, but you could say that it's possible that the surface here on the benzene ring that is more that has extra electron density is larger than the surface on the water molecule that has extra electron density. So it's possible there's just more space for an interaction there. I don't know, but that seems reasonable. Okay, other questions? So let's just, in dealing with non-covalent interactions and the issue of how strong they are, it's useful to think about two different things. So let's just go ahead and continue on in this sort of dissolving reaction. So we're taking crystalline sodium chloride and water, and then we're dissolving them such that each sodium ion is separated from chlorine by some distance, and each sodium and chlorine ion is interacting with a shell of water molecules engaging in ion-dipole interactions. Over here we had ion-ion interactions, and over here we had ion-dipole interactions. Now, in considering equilibrium constant, and when we talk about equilibrium constant, really we're also talking about free energy. Delta G equals minus RT ln K, where negative delta G numbers mean equilibrium constants that are favorable and in the forward direction. One of the things you learned that in general chemistry is that there are two things that affect free energy. One is delta H, which is called enthalpy, and the other is delta S, which is called entropy. Now, I remember learning about this kind of stuff and having a pretty good idea of what entropy was, but absolutely no idea what enthalpy was. Maybe you guys are backwards from that. I don't know. What is entropy? Disorder, randomness. The entropy can be related to the number of different ways to rearrange, in which it is possible to rearrange a situation. So which of these two states, before in the solid versus in the dissolved state, which of these has more entropy, do you think? After, right? Because there's only a few ways you can arrange sodium and chlorine ions in a crystalline lattice. There are many ways, perhaps infinite or close to, many, many ways to have sodium surrounded by water molecules and chlorine atoms surrounded by water molecules, and they don't have to be close to each other. They're free to be moving in any direction. So we would say that in terms of entropy, after this process we have more disorder. Before the process we have less disorder. Okay, so that would mean that for dissolving, as we've talked about here, we would predict that delta S is positive. The effect that has on free energy, because it's minus T delta S, is a positive delta S makes the free energy move in a negative direction towards more favorable. All right. And Often there are offsetting effects. We haven't talked about water. Water molecules were perhaps freer before this process than they are after, in which they have to surround the sodium ions. Nevertheless, on the whole, for this process, entropy change is probably favorable. Now, what does enthalpy mean? Any ideas? Yeah, go ahead. The energy of molecular interaction. So you know something that I didn't used to know. For a process, the change in enthalpy is related to the energy of interactions that are formed as a process occurs, or also the energy of bonds formed versus the energy of interactions or bonds that are broken. So the question for enthalpy is, are the interactions that I form stronger than the ones I had to lose? All right? And for the question here for dissolving, you used to have before, you had ion-ion interactions in the solid, and then for water, you had dipole-dipole interactions in liquid water. Afterwards, you still have, in the water molecules that aren't surrounding ions, which are most of them not surrounding ions, you continue to have dipole-dipole interactions. And then for the ions, you replace the ion-ion interactions with ion-dipole interactions. Now, each individual ion-dipole interaction is weaker than an ion-ion interaction. But if you got a lot of those ion-dipole interactions, maybe you compensate entirely and then some for the ion-ion interaction that you lost. Okay, I'm replacing a handful of favorable interactions with a lot more less favorable interactions, but more of them. So probably our enthalpy for this process is also, oops, that's the wrong letter. Probably our enthalpy for this process is also negative, also favorable, because we have more ion-dipole interactions than we have ion-ion interactions. Okay? So this is more nuanced than just is it strong or is it weak. You have to consider both the strength and the number of interactions before and after a process, and then also the change in enthalpy as a result of the process. Go ahead.
So in this
Gibbs free energy would be negative here. What does that mean? That means, let's see, if delta G is negative, delta G equals minus RT ln K, or K equals the number E to the power of delta G over RT. If you have a negative number here, that means you're raising the number E to a positive number, which is going to be a large number greater than 1. And so equilibrium constant greater than 1 means it's favorable to go in that direction. Yeah. Now, I'm not going to have you calculate natural logs. I'm also not going to have you, really calculate delta G's at all. But the trend, the idea of what enthalpy means, and that if you, in a process, you make more favorable bonds or interactions than the ones you lost, that's favorable for enthalpy. If you get more disorder versus what you had before, then that's favorable for entropy. It's difficult to predict how entropy and enthalpy offset each other. And fortunately in OChem, at least in this class, we'll spend most of our time thinking about enthalpy and the strength of bonds, and a lot less time thinking about entropy. But the balance between enthalpy and entropy is really important in biology, really important in biological processes. There's a couple more things I want to deal with non-covalent interactions. I know we should be moving on to chapter 4, but I just really can't resist. So we'll pause now. When we come back, we're going to talk about why oil and water don't mix and why lard is a solid but olive oil isn't. Okay? So let's pause and we'll be back in about 5 minutes.